First Spin. Welcome to First Spin, a show where I learn how to use the parallax propeller without having any prior programming experience. And rather than do this on my own, I have enlisted the help of two experts.
She beats us with sticks.
Sometimes.
It's painful. Very, very painful.
Only when your explanations are subpar. And then I have to
beat us with more questions.
Correct.
And more questions is a stick she has that has more questions written on it. Beats us over the head with.
Everyone's going to think I'm abusive, but how could I be abusive? I'm the noob.
All they have to do is listen to the past episodes of you abusing us with your questions.
Hey, you guys signed up for this.
Most noobs would be they would be very happy to be able to ask us questions, but not Addie. She hits us.
Just to keep you guys in line. You know.
So I guess we're glutton for punishment. What do you have for us this week, Addie?
We are continuing the ping sensor. Huzzah!
I thought we covered that pretty thoroughly. Did we?
Well, we did. Okay, so we did some of the hardware, and we did the concept behind how the ping sensor works. But we haven't actually gone through the first spin code.
Okay, so the spin
So today
code itself.
Is code. But I think there's a couple of loose ends we wanted to tie up from last week.
Yeah, one thing to definitely do with a ping when you're hooking it up to a propeller or any 3.3 volt microcontroller, you want to have a resistor between the ping and the input pin and / output pin of the propeller, because the ping's output is a 5 volt output. And so you want to use a resistor to just bring that down. And the propeller is set up so that it can actually work reasonably well with just a resistor to bring it down. Yep. Some microcontrollers, you might need to actually use a level translator.
Oh, wow. That's pretty hardcore.
But most of them can deal with some variance in the voltage if you just have a protection resistor in there to bring the voltage down and protect the pin a little bit.
Okay. And the one that I use is a 1K resistor because it was available. Yeah. And it seems to work. So.
Yeah, you can use a 1K or a 3.3K. Typically, we'll both, somewhere in that range of 1 to 3 or 4K is reasonably good.
Right.
Mm-hmm.
Okay, so we're probably going to cover a little bit of what we did last week, but that's because we'll be going through the code this week. And this week, I wanted to see if we could look through the ping object.
Mm-hmm.
And I have version 1.2. I believe that's it comes with the prop tool 1.3.
Yeah. So when you install the prop tool, you get a whole bunch of spin files, and they're in the propeller library folder.
Mm-hmm.
And one of them is the ping.
Correct.
Ping.spin.
Correct.
The code for reading the ping sensor.
Right. And I think you told me once that ping is easy enough to not have to use an object. So I wanted to see if I could not use an object.
Yeah.
By analyzing this one.
If you look at this object, it's actually a really tiny amount of code. It's really only like about 10 lines of code to actually read the ping.
That's what he says.
It is.
It's like a mountain. It's a mountain of code.
There's like, if you look at the ping.spin file, if you take out all the comments at the top and the comments at the bottom, there's only about 20 lines of code, and half of those or a quarter of those are blank lines.
I guess so. I suppose so.
So, right.
I suppose. All right. So, if we could can we just go through it?
Yeah.
Okay.
No problem.
So the con section, we have 2in, 2cm. So
and what's the file name on this, so people can find it in their
ping.spin.
And which directory does it live in with the spin tool stuff?
So in your propeller tool version 1.3 directory, which is in your program files, Parallax Inc., there's a library directory, and in there is the spin file.
Right.
And if your installation is older, it'll probably be up in the top level. But it would have to be pretty old, like mine.
Yeah.
You should update yours, Whisker.
I know I should, but I mean, I've been using these propellers for so long that I kind of know where everything is, and they changed it all, and you know how that is.
But
get off my lawn!
They fix things in the newer version of the tool, though, so you might need to update at some point.
Yeah.
Okay. So the con section, we have the 2 in, which I guess is 2 inches, and then 2 cm, 2 centimeters. I'm guessing there's a conversion there. Now, the 73,746, is that number of clock ticks per inch?
Right. So it's how many clock ticks go by.
Or clock cycles, actually.
Well, it's the increments of the count register, right? The CNT register, which is your system clock. Okay. So how many times that ticks?
How many system clocks per inch?
Right.
Okay.
So there's 73,746 system clocks go by. Now, when you're going 80 megahertz, there's 80 million clocks per second.
Mm-hmm.
Right.
So this is very small.
This is like, it's pretty small, right? Yeah. You're talking about 0.0073 seconds.
Right. That's cool.
It's very small.
Cool.
Yeah.
Okay. And then centimeters, it's 29,000. I can't even read numbers. 29,034 system clock cycles per centimeter.
Right, and that's just normal math. There's 2.54 centimeters per inch, so it's basically, some portion of an inch's distance.
And this is something that we get from the manufacturer, right?
Well, it's just, it's basically the speed of sound travels that far in an inch, right?
Okay.
How long it takes.
Okay.
In clock ticks.
Gotcha.
Because 80 million ticks per second, 0.00737 whatever seconds is how long a sound wave will travel in an inch.
Okay.
How long it takes.
Okay. All right. Beating dead horse. Sorry. Right.
Yeah. Very basic, distance time thing there.
Right. Okay, and then ticks, pin, microseconds with local variables CNT1 and CNT2. This returns the ping's one-way ultrasonic travel time in microseconds.
Right. So there's a little bit of math at the end that turns the clock tick counts into microseconds.
Okay.
Which is just doing division by how many clock ticks per microsecond. Right?
Okay. Yes. But we'll get there. We'll get there.
Right.
We'll get there.
Right.
Okay. So, remember last week we said that the process is that the pin, the propeller pin is set as an output, then set high, then set low, then set it as an input. So output 1, 0, input. So this outer pin tilde. Gosh, it's been a very long time since I've
so the single tilde following like that is to clear it, to set it to 0.
Oh, okay.
So they're just starting off, like a lot of their code will typically start off by just clearing the output pin, to whatever pin you're dealing with, they'll just clear it to 0, and that's what they're doing there.
Okay.
Right?
Okay. And then the DIRA is actually setting the pin as an output.
Right, because it's got the 2 tildes, which is to set it on. Set it to 1.
No.
Yes.
No. Dir A is setting it as an output, period, without any power yet. Out A is setting the power to it.
But when you set the Dir A register, you're setting it to 1 to say it's an output. That's the Dir register, not the out register, the Dir register, which is setting the direction of the pin. That's all. It's just which direction is the pin? Is it an output or an input? That's all we're doing.
Right. I know. That's what I'm saying. Yeah. So Dir just sets it as an output or input, period. It doesn't say whether it's sending a 1 or 0 or anything. Right. So Dir tilde is an output, period.
Right.
Out A pin tilde means it's setting 1.
Right. Setting it high.
It's setting it high. Right. Mm-hmm. So sending a 1. Then out A pin single tilde is doing the 0.
Right. And now one thing that I want to add in here, because this is spin, the fact that it's setting the pin high and then setting it low, one line after another,
Mm-hmm.
spin is not super fast.
Mm-hmm.
So that's actually several microseconds goes by between each line in the spin code.
Okay.
So, or at least, a few microseconds goes by.
Mm-hmm.
So that 2 lines there on the propeller, it's allowed it to actually go high and then go back low with several microseconds of it being high in the middle.
Okay. Okay. Gotcha.
In on another microcontroller, they might actually have to put a delay in between those two.
I see.
If it's, depending on how their microcontroller
How
works.
fast it works, I guess.
Right.
Okay.
Right.
Okay.
If this were in assembly instead of spin, we would have to have a delay.
Okay.
But that's just so you know.
Yep. Okay. Good to know. Good to know. All right. So setting at 1, setting at 0, then it's setting the DIRA again is just input or output, and it's setting as an input with that single tilde.
Right.
And that tells the ping sensor, oh, time to wake up. And essentially the propeller waits for the ping sensor to set the pin high, right?
Mm-hmm.
And it's with this wait PNE code. And this wait, or command, I should say. And the wait PNE is wait for the pin to not equal, like NE, not equal. Right. And then the 0 is the value. So wait for the pin to not equal 0, comma. And then what's this? I know we've gone through this, but if you could refresh.
It's the decode value. So what it's doing is it's taking that number that's the pin number and setting that bit high in the whole D word, in the whole long, right? So
that's the pin to
actually compare against.
Okay.
So the wait PNE command could actually wait for many pins, all 32, to be in a specific state.
Oh.
What you're setting there is you care about the pin that whichever pin you care about, which let's say the ping is hooked up to pin 10. So pin is 10 in this case. It would set the 10th bit in the long high, and that's what it would pass into the wait PNE as along with the 10th bit on.
Okay.
Which equals compare that 10th bit with my value.
Okay.
Right?
So pin. What we said, was it 0?
10 in this, we're pin 10 is
pin
what
10.
Our example was.
Okay. All right, pin 10.
Right.
So wait for the pin 10 by looking at that middle value to not equal 0, which means equaling a high. And then what's that last 0?
The last 0 is which port.
Oh,
we went over this before. 0 is port A and 1 is port B, but on the propeller chip, there's no port B.
Right.
So
right. Okay.
You always pass in 0 to the last parameter, wait PNE and wait BEQ.
Okay.
And if you focus on that, you can actually bend spoons.
That's true. Thank you, Whisker, for your contribution.
Yep.
So this wait PNE line is waiting for that pin to go high. It's waiting for the ping to send back the signal, high, saying it sent out the chirp.
Right. And then when it turns high, then CNT, the current system clock cycle, is recorded into the local variable CNT1.
Right. And just to clarify so people understand, the wait PNE instruction in spin is going to sit there and wait for that pin to go high. It's not going to go to the next line. It blocks is what they call that.
Okay.
It will stay on that line in the spin code waiting for that pin to go high. And as soon as the pin goes high, then it will go to the next line.
Okay.
And if it never goes high, it never goes on.
Right. It will wait forever.
Forever. I'm sure there's like a time stop.
Well, it'll wait until there's no more propeller power. Right?
Yeah.
Till the end of time.
Till the sun explodes and the earth gets enveloped in the fireball and you don't have power to your propeller anymore.
Only 7 lines, 8 lines.
Right.
And the world can. Okay. So then we wait.
First spin, we destroy the universe.
Yes. Then wait.
So we record that first time into CNT1, like you said.
Right. And then wait PEQ is wait for the pin to equal. And then we'll look at pin 10. and wait for the pin to equal 0.
Right.
So that's
PEQ is the exact opposite of PNE.
Okay.
Right.
Yep.
So PNE is waiting for not equal, and PEQ is waiting for it to be equal.
Right. So the pin goes low, and then that equals 0, and that's again set by the ping sensor when it receives the chirp.
Back.
And then the propeller takes the current system clock cycle and puts it into local variable CNT2. Right. And then it takes the difference of that amount of time, and because we want to see...
So just to go over the next line a little bit, because it's got a couple things you might not be familiar with.
Right.
So it's saying microseconds : equals, and then it's got those 2 vertical bars.
Absolute
what that
value
means is absolute value.
Yeah.
Very good,
Right?
Eddie.
Thank you.
So it takes CNT1 minus CNT2, which gives you a value of the difference in the 2 values, and then it absolute values that, because that's all we care about is the
difference.
The positive difference, right?
Right.
Not
or the delta, as it were.
The delta, yeah. Okay. And then what it's doing, the next thing it's doing is the clock frequency divided by 1 million there.
Yeah.
Is saying, we want microseconds, which is 1/1,000,000th of a second. And clock frequency is how many ticks there's going to be in a second. So if we divide that by 1,000,000, we get, in this case,
the number of clock ticks in a microsecond.
Right. And so we're going to divide our delta value, the total time in clock ticks, by, in this case, 80, because our clock frequency is 80 megahertz. 80 million divided by 1 million leaves 80. And that will give you the number of microseconds that the chirp was traveling out and coming back. Then the final thing it does is shift it over by 1. And we went over this before. When you shift over by 1, that's the same thing as dividing by 2.
You remember bit shifting, right?
Yes.
I think you just bit shifted Eddie's brain.
Yeah.
So, you know what it is? It's because
it's powers of 2, right?
Yes.
So each one you shift is dividing by 1 more power of 2 higher, right? So shifting by 1 is dividing by the first power of 2, which is 2.
Right. I think we went over this.
Right.
So you divide it by 2 to get the one-way amount of microseconds.
This could also have been written as divide by 2, but it's just slightly faster in spin to use the shift down by 1, because it's a faster operation.
I see.
That's why
And I think my brains was hung up because I was trying to figure out, how in chemistry you learn getting your units correct and canceling out. I wish I remembered the actual name of that. And you cancel out the units to get the correct unit for the answer.
Right.
Does that make sense?
I know what you're talking about.
So I'm trying to figure out going from the seconds to the microseconds. And here they're dividing it, so I have to get the flipped, the inverse, or whatever you call it, of that in order to cancel out the reciprocal, in order to cancel out the seconds.
Right. But what they're doing here is they're taking it from clock ticks to microseconds.
You're right.
With that division.
You're right.
And then they're dividing it by 2. And the reason they do that is because the time is the total time that the chirp went out and came back. But what we really care about is just one way. How long it took to get out to whatever it hit.
Right. So now we have a microsecond number of microseconds for
that the
a
chirp
one-way
was traveling till it hit something.
Right. So let's say we want to do inches. Okay.
Which is the very next pub function.
Right. So distance.
How convenient.
Distance : equals the ticks. So that's actually, the pub should be called microseconds, right? Instead of ticks, because it's not really the clock ticks, it's actually microseconds.
Yeah, but they call it ticks. It's microsecond ticks instead of clock ticks. That's what that is.
Okay.
It's common. It's somewhat common, although not necessarily fully accurate in computer land and
Okay.
microcontroller land,
Okay.
to treat microseconds as ticks.
Okay. So the microseconds times 1,000 to get. I don't know. What's microseconds times 1,000? What does that take us to?
Milliseconds.
Milliseconds. Milliseconds, and then.
Yeah. Yeah.
Okay. And then divided by the clock ticks per inch.
Right.
So are those is
not
this
clock ticks by microseconds per inch, right? Let me. I haven't actually fully looked at all this part of it, so I'm not quite sure why it ended up. Let me think.
Do you see
So
what I mean, though? Do you see
yeah.
yeah.
It's the time in microseconds. So the time in microseconds times 1,000. Huh.
And
I guess
divided by the ratio to inches.
Right.
Which is 73,746, just a constant defined up above.
Right. No, I understand that part, but
we're trying to figure out the correct units.
No, I know what they're doing. So think about it like this: 1,000 divided by 2 inch is the fraction of 1,000 microseconds.
Yeah.
Equals that many. The 7. It's doing a conversion, and so it's doing a 1,000 divided by 2 inches is the same thing as divided by the inverse. It's I'm sorry. I'm making it more confusing.
I see what you mean. It's right. Automatically doing the reciprocal for you.
Yeah.
Because that's like a rate. So you're actually taking the time, and this was actually what I was going to say before Whisker interrupted me last time. So when you measure distance, okay, you have two pieces of information. You have time, and then you have a rate, a velocity, right? So what you end up doing with these two pieces, and the velocity is like distance over time, right? So you have a time and a distance over time. So to get your distance, you multiply these two pieces. Yes?
Well, you divide, but multiply, yeah.
Well.
So
no, you multiply.
Well, the time divided by the rate equals the distance.
Time divided by rate?
So
yes, okay, yes, you're all right.
The rate that it's moving is some, number of ticks that it's moving. And then the total time divided by that equals how far it went.
So the rate is the 2 in over 1,000 microseconds.
Right. No, 1,000 divided by 2 in.
But you're dividing it. So this is the reciprocal of it.
Yeah, but look at the code. The code is ticks pin times 1,000 divided by 2 in.
Right.
Or the other way to think about that is 1,000 divided by 2 in times the number of ticks.
Right. Or
and the
ticks,
2 in is the 2 inches conversion.
Or ticks divided by 2 in divided by 1,000. Wait.
Oh.
I think y'all are making this way too complicated.
Right.
So like we've got the inches one there, and the next one down is actually just a converter one, but the one after that is for millimeters, and it does the same thing there, where it's going the distance is equal to ticks pin times 10,000 this time, and divided by 2_cm, which is, obviously a different ratio to pop you into the metric system. And the previous one before it was the centimeters one, which basically just calls this millimeters one and does a divide by 10 to get centi instead of milli.
Right.
Pretty simple stuff. It works exactly the same as the inches, just with a different ratio because you're going into a different scale.
Mm-hmm.
And the rest is all comments. So, this is a really simple object that you've got here. other than the few little funny symbols like absolute value and bit shifting. It's fairly straightforward.
Right. So then, how easy would it be for me to just put this, like, write this directly into the code as opposed to using an object for it?
So if you want it, you could take the contents of the Tymkrs pub.
Yeah.
So that sequence of commands to out in wait PNE, wait PEQ, and get the microseconds, and then take the, like, if you want the inches one, then just take the microseconds variable that it assigns, and then times 1000 divided by 2 in, and that's your distance in inches. So you could just copy and paste the code into your function somewhere, wherever you want it in your code.
Okay.
And
can I ask a general question?
It's generally not a good programming practice to do that.
Mm-hmm.
Typically you want to leave it like this, where it's just some spin code.
Sure.
Because the way this particular object works is when you call that function, it's just running on the same cog that you're running on. It's like not using another cog or anything. It's the same thing as if you had copied it into your code.
Okay.
It's just more clean and easier for people to read. And if you wanted to use it more than once, it would be better to have it be in a function like this than to copy and paste it everywhere.
That makes sense.
Right.
And do keep in mind, I don't think you're not really stuck working in inches or millimeters or centimeters here. You could pretty much ignore those and base all of your stuff off of time instead.
Right.
And work in that sort of domain. But just to put that out there. Also, if I were to use this thing, I would probably write it so that it would actually spawn off in a cog if I had a free one, and then sit there in its wait states, and then return to a global variable. So this thing would just spawn off and take however long it takes, and then drop the information into a global variable instead of blocking my main control loop of my program.
Well, as an example, in the past, I had a robot that had 3 of these on it, and I wrote a single cog assembly program to read all 3 pings continuously and just save out the distance for all 3 to a global variable. Each one got their own slot in the global variable array.
Can I ask, how do you know if you're writing it for a single cog? Like, is each pub equal to a cog?
No.
Oh.
The only time that you would be causing another cog to be used is if you actually use the cog new command to cause a new cog to start up, and you pass in code to the cog new command, right?
Okay.
If you don't actually pass in, if you don't call cog new and pass in a code, then you're not starting.
Then you're all using it on one cog.
You're just using the one cog that you're already in with your main code.
Okay,
which is why I said I would probably redo this one, because this has blocking statements in it that wait for things. I would never call this directly from my main control loop unless I specifically wanted it to block, right?
Right. Because it could block for up to 18.5 or 19 milliseconds.
That's quite
which is it seems like a very short time to us, but it's a really long time for the processor.
For code, yeah.
Right. You could do a whole lot of stuff in that time period. So like Whisker said, I would definitely, my personal preference is to create a separate cog to do this.
Okay. So then
and I actually do it in assembly, because then I can get higher accuracy.
Sure.
Okay.
So then let me ask one more question. This is the last question I think we have time for. So say I forgot that you needed to use cog new to spawn off new cogs, and say I just stuck a whole bunch of code in one cog. Could it overflow?
Well, if it's spin code, it's actually not in the cog. Remember, it's only in hub memory. Okay. So you can fill up all of hub memory with one big giant program, and one cog, which is running the spin interpreter, like we discussed many episodes ago. It will just read that code from wherever it happens to be in the hub memory.
So I have a compass module, a ping sensor, and RC servo code all running on one cog, right?
Well, they're not
in one
necessarily.
program.
It depends on what object you're using to talk to each of those things.
Sometimes the objects automatically spawn off.
No. Let me see if I.
So, like the servo one is probably
right.
spawning a cog to read the servo, right? Or
no.
to write. Or are you using some of your own code?
I'm using my own code.
Okay.
She's a hacker.
But that's the one that it doesn't work. So the compass the compass module works okay, and the ping sensor works okay, but the RC servo won't move.
Yeah, well, see, part of the problem with an RC servo is that you have to keep sending the pulses fast enough, or it will just start acting like you're not talking to it. So one of the issues is that the pulses have to come at a regular rate.
That's why on other microcontrollers that aren't as multi, cord as the prop, they usually have to have some sort of outboard solution to control servos. Because you need to
I just need to spawn
keep
a new
PWM going.
Right. So what you need to do is control the servo in another cog using cog new to drive the servo, and then you can still do the ping and the other thing, your compass, all in the main cog, because those aren't dependent on getting the pulse at a regular rate. There are some servos that are a little less strict on that. Some of them would work with the pulses coming much less regularly, but a lot of them won't work unless you send the pulses at a continuous rate. You'll get either no response like you're getting, or it'll be really erratic and do odd things unless you send the pulses at a constant rate.
I hope that was a good enough explanation of that, because we're out of time.
Yes, that was adequate. Thank you.
Yeah, and hopefully next week, Addie will be able to reveal to us what her project is that she's been messing with this stuff on.
And I think we might also go over the 5-position switch thing.
Okie dokie. So, well, you guys can find this show every Tuesday at firstspin.tv.
Yes.
And we'd really like you guys to send in any questions about spin and related peripherals to feedback@tymkrs.com, and we'll try to answer those on the show.
Yep.
So we'll see all of you guys next week.
Bye.
Bye.
See ya.